Thank you, Nadav, and thank you everyone for joining. Yeah, so today I wanted to talk a bit about adaptive computer LLMs specifically with early exit. Yeah, I'm currently a research scientist at Google DeepMind. So also, if anyone listening is like interested in those topics, feel free to like reach out in general. But yeah, today what I'll go over is mostly based on, or only based on papers that we published, mostly paper from NeurIPS from a couple of years ago, and also a new paper from ICLR that will be presented in a few, like next or yeah, end of next month. Feel free to interrupt me in the middle if you have any questions or comments. I see that there are a couple of people here that I've already talked to with in the past, so feel free. I know we all have good ideas and comments, so really feel free to interrupt in the middle, and we can make it interactive. All right, so yeah, let's kick it off. So yeah, so first let's talk about early exit in general in LLMs. Just as a motivation, to set the stage, we know that in general, a good recipe for making models better is increasing their size. You increase the size, you get more capabilities, models that perform better, but unsurprisingly, it comes with a cost, especially during serving, where serving large models is expensive. And this is especially true when you do autoregressive decoding, because for each token that you generate, you need to go through all the layers of the model one at a time, because it's a sequential process, and that's what makes it slow. Now, what we're trying to do in this work that we call CALM, Confidence Adaptive Language Modeling, is for certain tokens not to go through all the layers of the model, but after a few layers of the model to already, sometimes the prediction is already good enough. So just to predict the next token and move on to the starting to compute the next one. And the intuition here is coming from the fact that like not all predictions have the same difficulty. So sometimes you need more compute and sometimes you don't actually need as much to just predict the next token. And we'll also see this verified empirically in our results. So yeah, so first of all, just very quickly, let's go over how to make models that have this early exit capability. It's actually pretty simple to add this capability to our language models. One way to do it, that's what we did in this paper that was based on T5 encoder-decoder models, is just to add this loss, like anytime prediction loss. So instead of the regular cross entropy loss that you do on top of the final layer, you just add for all layers, or we might decide to add for some of the layers, but for simplicity, we just added for all of the layers a loss. So you go during training, you anyway go through the full model, and then you have the activations from all of the layers, and you just take all those activations, project them on the same shared unembedding matrix, and get the predictions from all the layers, and then you just compute the loss on that. Now that's one way to do it, like just to do the average over all layers, and that's already like is giving good performance for lower layers. Like here, for example, we see the performance with. Can you see my mouse? Or I think maybe there is.
Yes, we see the cursor.
Okay, perfect. Thanks. So yeah, here you see the performance over training of a low layer of a model and the top layer. So by the way, like if you don't do this at all, then like the lower layer gets around 20% accuracy, which is also better than random. So you can even like not care about this at all during training and just try to do it during inference. You'll also get better than random performance from the lower layer, but it's still not very good to get 20% accuracy. But if you just add this loss, then you get much better performance from the lower layer and still pretty good performance of the top layer. And then if you simply don't, like, instead of average, you just do a weighted average where you prefer the higher layers, then you get the same performance for the top layer and still pretty good performance from the lower layers. So that's the training part, and then on top of it, you can also train a classifier. Like next, we'll discuss how you decide if to early exit. So one option is just to use like the softmax probabilities, and another option is to train an additional classifier on top of it in order to kind of like act as the router for deciding when to exit. Yeah, so as I was already saying, like now that you have a model that is trained for exiting at any point, during inference, you need to decide for each token when you exit. So here we examined a couple of options. One is just, to take the current intermediate activation, compute, the unembedding, the softmax, and just like compute the entropy, or even simpler, just take the maximum value out of the softmax. And this turns out to be actually a very good confidence measure that could be used for measuring if the prediction is ready for exiting. Um, Another option that is like very simple to compute is what we call state propagation. So, we have the hidden state at certain layer and then the hidden state at the next layer, and you just compute the distance between the two. And you can say that at some point, the hidden state stops changing and the layers act more like as a skip through, and you want to catch like that point. So it's a bit less expressive, but it's very simple to implement and fast to compute, and it's also like a good, out of the box measure. And the last one that I just said that you can do a bit extra training and train a specific classifier targeted at this decision. And you can collect this data on the fly, like basically run through the model and see whether the intermediate prediction is the same as the full model. And that will be like your on the fly labels that you use for training this classifier. So this is like for deciding how to exit per token. We'll also discuss how to like connect that with like the overall performance of the model. But another issue that comes up when you do specifically this early exiting for sequence generation is that, if you exit for one token and then you continue in generation, and then later on you want to go to a higher layer, then the self-attention needs to look at the previous tokens at the KVs from the same layer, based on like the outputs of the previous layer. But now if you exited, you're missing them. So it turns out that a very simple solution that works here as well is just if you exit, then your hidden state is also like good enough for the self-attention of the following time steps. So we just take that and like propagate it to the rest of the layers, or effectively when we at the future time step, we look back to KVs from to hidden state from lower layers. We do apply the KV projection of each respective layer in order to like get it into the same space, but we effectively look at the hidden state from the exited layer. Yeah, and another thing that we found out that could be helpful is that like it turns out that the earlier mistakes that you make are more detrimental, because if you make like you miss a token early on, then because of again the autoregressive nature, your whole output could go in the wrong direction. So it makes sense to be more conservative at the beginning of the generation. And then, towards the end, if you like, make a mistake in the last few words, then, it's also not the best, but it's not that, it's not that bad because at least most of your output is good. So based on that intuition, we also introduced this like decaying threshold where we're more conservative in the beginning. And then as we go on in the generation, we're allowing more early exits. And this allows like a better trade-off between the speed ups and the performance. Yeah, so now to talk a bit about how it performs. So we measured this, most of our experiments were on a T5X encoder decoder 8-layer model. We also experimented with larger models. And yeah, mostly just here on summarization, translation, and question answering, and data sets that have like different characteristics. and yeah, the typical evaluation metrics. Okay, so let's look at those results now. So the this point like is the regular model, like the 8-layer model if you use it fully. Now, what we call static, that is kind of like similar to distillation, where for all tokens you use the same amount of compute. So we can cut the model just to like 7, 6, 5 layers or so on. So obviously this will be like faster models, and we lose a bit of performance. But if we use this dynamic style early exiting, which is the solid lines here in different colors, then we get much better, performance per average number of layers. And the star here is kind of like the oracle measure. So this is like as if, this is like the upper bound that is like not really realistic, but like if we knew for sure at any point that this is like that the prediction at this point is the same as the full model, so there's no point in like continuing computation. And then we could get like the same performance of the full model with like on average only 1.5 layers, which is like pretty insane. So this is like the headroom that we have, and we don't get there, but we still get like pretty close to it with our just using our like proxy confidence measures. Yeah, and in practice, it also like nicely translates into speedups. And here we see like an example output of the summarization. And the colors here, they represent the number of layers that we went through the model for each token. So green means that we went only through like one or few layers, and the red tokens are the ones that use most of the compute. And the nice thing here, like I said, like, compared to like distillation where you just use the same model for everything, here the model kind of like naturally distributes the compute and only for certain tokens really use the full capacity. Mostly, beginning of sentences, like maybe some verbs and some like some instances that like really determine where the output is going. And for most of the tokens, you really don't need the full compute because like it's really easy for the model to just continue it. Yeah, so this is like the basics of getting early exits into language models. And next I'll talk about how to get those speedups while controlling the quality. But before that, any questions so far?
Hi, Tal. Maybe just a question about Oracle. Is it true that for Oracle, you exit at the first layer that has the same prediction as the full model, or that has the same prediction as the same token as the ground truth? So I'm just wondering, is it consistency Oracle or ground truth Oracle?
Oh, hi, Method. Yeah, good question. So this is based on consistency. Um,
Okay.
This is like, yeah, the first layer that the prediction is similar as the full model.
Cool.
And
Yeah, and maybe another question here is, because here like classifier consistently underperforms softmax, right? But I think it was one of your earlier works in CAT, it seemed like it was the other way around a bit, where the meta classifiers performed better than softmax. Was that the case, or?
yeah, you're right. In like so we found like the behavior to be slightly different between like the BERT style encoder early exiting and this language model. But one thing is that there, the classifier, we did enrich it with some extra features that we didn't really do here. Here it was a very simple linear classifier. In the encoder early exit, we also augmented with some kind of like meta features based on like the history of predictions. And I think there it was also a 2-layer nonlinear classifier. So it ended up being a bit better.
Okay, so could be that I see the meta feature or the additional features there were the reason for better performance. Okay, because here is just the intermediate representation, right? Nothing else.
Yeah, here it was very
Okay.
simple.
Okay.
And yeah, there's I think there is some headroom. Yeah, to be honest, so there wasn't we didn't exactly try to optimize the classifier here.
Okay, cool. Thanks.
Yeah, thanks for the question. And yeah, just another comment about the Oracle measure here, just since we discussed it, to clarify. So one thing about the Oracle, because of like what I was saying about the KV cache potentially being missed for future predictions, then this is true also for the Oracle. So like we exit at the earliest possible layer, but then later predictions will need to rely on this hidden state as well. So like potentially the Oracle is not guaranteed to keep exactly the same performance as the full model, though in practice, at least in those evaluations, we see that it does. So that's another evidence for the power of this like KV propagation of the exited layer. And yeah, like Method pointed out, like generally we see the softmax to do better, but the softmax can be a bit more expensive to compute. So like if we take that into account, then also like the latency that it takes to compute the softmax versus just like the binary classifier, then actually the classifier sometimes is doing a bit better because it's like faster to compute.
I have a question. Thanks for the very interesting work. Is this just for like batch size one, presumably? Because you need to stop. You need to early exit for all of the tokens in the batch at the same layer, presumably.
Yes, that's a very good point. Yeah, this is batch size one. There is still some
I'm just
applications.
thinking from a sort of inference inference performance standpoint, you rarely would 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 use batch size one, I guess.
Yeah, so first of all, the second part of the talk will address exactly that, like how to try to do early exit with larger bets. So stay tuned. And yeah, irrespective, I think that there are still some applications that use batch size one and can benefit from this.
Okay, cool. Thanks.
Yeah, thanks for the question. And yeah, it's always good to clarify that those results are for batch size one. All right, so yeah, so let's dig in a bit to like how to preserve the performance, and then afterward we'll talk about like how to apply those early exits into like large batch settings. Right. So, okay. So we talked about like, how to train those models to exit, how to like decide based on some confidence measure, like when to exit per token. But like now, how do we actually use it in a way that that we don't lose too much of the quality of the model that we have? So we need now like to basically calibrate when do we exit per token. So, there are a couple of options we can do, just decide on some threshold that we believe in to try to like calibrate it with like flat scaling and so on. Or what we did here is to apply like more, more like grounded techniques like conformal prediction, where we can get more specific guarantees on the capability of the model. So a very quick like crash course in like 2 slides about like what is a conformal prediction without going into like all the theoretical details, but like the main idea there is that you want instead of only predicting one class, you are predicting a set of classes. And what you want is that the true class, which is y, will be within the set with high probability, or 1 minus epsilon, where the epsilon is like the tolerance that the user can specify in order like to like control how strict they are about the requirement. And obviously you want this like set to be not too large, because like the naive solution is just to return like the whole label space. But you want to the set to be like as small as possible in order like to be efficient, to be like a small set, while still still maintaining this guarantee of the true label being in the set with high probability. So, just as a quick example, you have some input, like let's say that it's like image classification, you have your label set, your label space, and then you want to output some prediction set that like the correct label is within it, let's say 80% of the time, the correct label is within this output set. And to create this set, you basically like have to define some kind of like non-conformity measure, which is similar to like your confidence measure. So, one thing that you can take is just like 1 minus the probability of that specific class, or like when we're talking about the softmax, so you take just like the 1 minus the value of the softmax. And that could be like your non-conformity score. And then you have some kind of like calibration set. You collect all those scores for the calibration set. And then you just simply take the inflated quantile over that those scores that you collected. And basically you define lambda to be that. And then you construct your prediction set by all the measures that are smaller than lambda. So if you follow that like simple recipe, you get this guarantee. Now, how do we tie it back to early exits? So yeah, the first work that came up few slides ago in the discussion that we did it for was in classification. So in classification, it's a bit like more simple setup because we don't have a series of predictions. We only have like single prediction per example. And again, what we want is like, let's say that like G is our model with early exits and like F is the regular model. So we want G to be equal to F, at least 1 minus epsilon% of the time. So, now how do we apply conformal prediction to it? So, as we said, like, you get like a set of predictions, but here what we are looking for is like the minimum, like the first layer where the early prediction is similar to the last layer. So if we like simply apply conformal prediction, we end up like with a set of layers, but, we don't know which layer, which answer out of this set is like the one that is actually good for us. So we won't be able to really get this guarantee that we're looking for. But what we did here is actually to just like flip the set and to create a set of the layers that don't agree with the last layer. And then if we like take the first layer that is not in that set, then we exactly like know with high probability that this layer is like consistent with the full model. So yeah, that was a very like a nice trick to get it to work with the conformal prediction guarantees. And like in practice, the inference algorithm is like pretty simple. After you do this calibration, you just go through the layers of the model, and each one of them is like effectively like a hypothesis testing. And then like for if you can reject the hypothesis that they are inconsistent, then you just return that layer because you know it's high probability that they are consistent. Yeah, it worked like pretty nicely in classification. Like those are usually the plots that you do to empirically validate the conformal prediction. So on the x-axis here, you have like the user tolerance, like the 1 minus epsilon. So here, let's say that we want 80% of the time, we want our model, our early exit model to agree with the full model. So we plot the diagonal, and if we are above the diagonal, then indeed we met the guarantee that we provided to the user. And as I said, like we want to like still do it while being as efficient as possible. Like in our example of early exits, then we want to do it with as few layers as possible. So that's what we see here, that like if we meet the guarantee but do it like with fewer layers, then we get a good algorithm. And yeah, here like indeed like the classifier, which we call here the meta, was doing a bit better than the softmax in this case. Okay, so that was for classification. And now let's tie it back to like, how do we do it for a sequence of generations? So we want, again, like to get the same kind of guarantees. We want like the full output to be, not too different between the early exit model and the full model. And we want to provide these guarantees, but still like exiting as early and as frequently as possible. So yeah, the secret here is just like to define exactly this like in more formal way and like to just calibrate for it. So we define two ways to control for it. One is with textual consistency. So in textual consistency, we kind of like, we bound the difference in some kind of textual space between the early exit model and the full model. And this, like, we don't need any label data for it. We can just, on the fly again, collect generations from both options and just measure the distance between them. Or if we do have label data and we want to control for the risk, like for, for the difference, for like the drop in root score or something like that we get from the early exit model, then we can also do that by like simply, again, defining this difference between the early exit model and the full model, and bounding the difference between the two. Yeah, and then the algorithm is very similar to the classification. Again, we just go through, like for each time step, we just go through the layers and basically look when we exceed the threshold. And to tune the threshold, and here again, we use like the conformal prediction techniques, but like because this is a bit of a different setup, then we use a framework called the learn and test. And I'll skip like the technical details here, they're in the paper, but like it's a very simple calibration process. And if you follow that, then you get the guarantee. And yeah, you can check it both mathematically in the paper and also like empirically. Again, we can plot this same kind of plots. Here we want to be below the diagonal because this is like the distance, it's not the consistency. So we are indeed below the diagonal, and yeah, we measure like similar to how we saw before, like the softmax. Here, the lower the better is, and the softmax is a bit better in terms of like using fewer layers while guaranteeing the same performance. Yeah, and again, we can like still get nice gains both in terms of like flop reduction and the actual speed up, while providing the user this like guarantee that the model is like not too far from the full model. Yeah, and we already like went through one of those examples, but like, yeah, basically now what I want to say here is that we're also giving a nice knob for the user, like with this kind of like guarantees to control how far do you allow the early exit model to be from the full model. And then, by like the user defines that, and then from that, you're doing the calibration process to like tune the exact threshold that you want. And based on that threshold, you might get like different kind of outputs. And like, generally, as you allow the early exit to diverge more from the full model, then you'll get faster models. But maybe the predictions will be slightly worse. But yeah, it can be like as worse or as close to the model as you want. And yeah, this is just different examples on the summarization, translation, question answering. And yeah, that's basically like how you do it, like how you do early exiting while providing some guarantees on the performance. Now, okay, let's like go back to like, looking at the general picture and like look at this illustration. This is, just like, hand wavy visualization of like where does this stand compared to other methods. So, we started from a vanilla language model. We have high quality and, but it's not very fast. So, we want something faster. So one option is, distillation. We make it faster, but we lose some quality. With our method, we make it potentially even faster, and we lose less quality and with some guarantees. Now we can further improve on that with different methods. One by method that is here in the audience is by leveraging some additional behavior of these like early exit models that like basically you know that on average the model is getting better as you go up the layers. So you can leverage that in order to get tighter bounds on your guarantees. And yeah, that was like very nice work that like basically, you know, you don't lose anything, you just get tighter bounds. And there's also some other methods to like better handle like the KV projection that I was talking about. And yes, a couple of other follow-up works here that I didn't cover here, but like also basically improve on that and give even better performance. But as was pointed out before, like one limitation is, you know, the other methods do naturally very easily support large batch sizes, and all those methods are, you know, basically for only batch size 1. So, you know, how do we go now and apply it when we have large batch size during inference? One naive way is you just aggregate across the batch, right? You know, you have a larger batch, you just like take the average confidence measure over all samples, or you know, you are conservative, you're going by the like the minimum confidence across all the examples in the batch. That could also work, you know, as long as the batch size is not too large, but you know, it quickly becomes not that great because, you know, as you might imagine, if you have like high diversity in the batch, it doesn't really hold to apply the same policy for all. So another thing that you can do, it adds a bit of like complexity, is to try to like rearrange your batch and to apply the compute only for like some of the examples in the batch and for some others skip. But most accelerators don't really like handle this very well, and it adds a bit of like overhead to do this conditional computation on the fly. So it's also not that ideal, right? So you can do that, but like you definitely like lose a bit of the speed. So one other way to do it is to apply techniques like self-speculative decoding. And the nice thing there is that you also are guaranteed that you get exactly the same quality. The cost is that you're actually applying more flops, so you lose some speed up. And just to like describe why that is happening, so you know, in speculative decoding, if you're not familiar, you're basically still using the full model, but you're using it in parallel to using a separate smaller model. So you use the small model for predicting a few steps ahead, and then in parallel, you run it through the full model and you accept until the last token that they disagree with. And the reason why it gives speed up is because it's leveraging some limitations of like most all accelerators, that like you have some unutilized compute here, because if you operate in like small batch sizes, which is like effectively what you do in decoding, because you decode only one token at a time, versus like when you do like the encoding or like prefill over long sequence, you have a lot of tokens that you compute in parallel. And then during decoding, mostly you have this like like the accelerator is not really fully utilized. So you can better utilize it by predicting a few tokens ahead and then running them in parallel. But in practice, you're using more flops. So, you know, there's no free lunch here. And there are a couple of papers. One of them is called Layer Skip, that actually like uses the idea of early exiting together with speculative decoding. So here, like instead of using a separate model for drafting, they use the early exit of the large model for predicting ahead, and then like the rest of the model for the verification. So yeah, so that's, you know, that's back to like visualizing like in general the space of options that we have. But now like there is a question of, you know, how can we actually reduce the number of flops and like maybe fully utilize the potential of early exits and get like, you know, even more speed ups with the same quality. So that's what I'll talk about next, unless there are any questions before.
Maybe I just have a quick question about layer skip. How do they determine the amount of layers they do in kind of drafting? Is it based on confidence thresholding, or is just like a preset parameter right on the left? How do they decide for layer 3?
Yeah, I think so. So this is not my paper to clarify. And yeah, I think from what I remember that they just set it as like a hyperparameter, that it's not like dynamic like we discussed before.
Okay, cool.
Yeah, so yeah, indeed, like it feels like there is more that could be done in order to like, get the full depth dynamic behavior here. So yeah, so how do we get actually this like flop reduction? So that's what motivated us to look into this work that we called relaxed recursive transformer. And this is like work that was led by an intern, Sungmin, that will be presented at ICLR next month. So, circling back here to what we were discussing, we have a batch of examples, and maybe for, one of them we want to exit early, but for another one we want to do more compute. So we're facing this issue of like, if we just apply it naively, then the first token will need to wait for the second one. But actually, like a similar challenge that we're having in general is also like for early stopping of generation. So like forget for a second about early exiting. When we generate in a batch, we have, examples that stop generating at different times. And then, back in the day, maybe the naive way would have been to like wait for the last example to finish. But nowadays there is this technique called continuous batching, where whenever one example finishes computation, then we can already like start computing another example instead, and not wait for all of the batch to finish. So maybe, we can apply the same thing also in the depth dimension. So, in this illustration, this is like a toy example. Let's say that we have a maximum batch size of 32, and we have a model that we break into 3 stages. So if we have now a stream of inputs, let's say that we first get 16 examples, we start computing them. Now we're getting another batch of 32 examples. We will need to wait until the first batch is finishing all of the stages, and only then start computing. Now, let's assume that we can batch examples from different stages together. Then here already, after the first step, when we get more examples, we can combine those 2 stages together into like a unified batch and save some time. Now, circling back to early exits, if we also like exit after some stages, then we free even more space and we can squeeze in more examples sooner, and overall like increase our throughput. But how do we actually do this in practice? Because it's not that simple to like batch together examples from like different stages in the model. So to resolve that, we come back to the idea of parameter sharing. So this idea was already studied a bit in the past. There are some work like Albert for classification, universal transformer for decoding, and most of them were just like using a single transformer layer and just repeating it many times. And it turns out that there are a lot of benefits and a lot of like very nice features of model that are trained this way. But here we really wanted to do this while preserving most of the capabilities of these very large models. So like our work here was taking a large capable model and try to convert it into some form of recursive model that can allow us to apply this like continuous batch-wise, continuous depth-wise batching, and to get the speedups. So yeah, this is actually like a recent or 2023 paper that studied a couple of like these different layer sharing techniques. And it turns out like the cycle approach, the way they call it, is actually doing pretty well. And it like also works well with where we're trying to go here of like having like the model repeat a couple of stages sequentially. So, the idea here is just to like, if you have a model of 6 layers, you just break it into 3 and 3 and repeat it twice. So yeah, so in general, this is what we call the recursive transformer. And the main things we addressed in this work is how to train it effectively. So yeah, one way to train this model is, just to like start from scratch, train it, maybe like train it with distillation from another model, but this could be pretty expensive. So as I said, like we can assume that we already have a large model that is capable. And instead of training the recursive one from scratch, we can just convert it in some way to this recursive form. So we explore different ways to do it. And we define like these 3 methods. I'm sure there are, sorry, I'm sorry, one second. Yeah, back. So I'm sure there are more ways to do it, but like at least we explored this. So one technique that we tried is what we call stepwise. So like if the compression factor is 2, then we take every other layer. And we always keep the first and last layer because they are more important. So so we already have a model. We just, we just keep some of the layers, we throw them out and take every other layer and keep the first and last. And that's how we start the training of our recursive one. Another way that preserves all, like, or utilizes all of the parameters of the original model is just, to average the weight. So like this layer will now act as 1 and 4. So we take layers 1 and 4 from the original, average all the parameters, and just start from that. And the last simple approach is, just to like throw away the upper half and just take those layers and repeat them. So yeah, so we did a bunch of experiments on Gemma, Tiny Llama, Pythia, and sorry. And a bit, and we measured on perplexity and accuracy. And yeah, we basically wanted to determine like what is your best way to initialize this model. So in this plot here, you see like the number of training tokens and the training loss. And one thing that's just as a reference is we took the full model and continued training it. And obviously, it gets the best loss because it has like all the parameters, but, we're not, we're aiming just to do as close as possible to that, but with a smaller model. And the other naive baseline is the random, as I said, like, so we assume that we don't have the full model. We just, start training this recursive one from scratch. And this obviously is like, not doing that well. But seems like, if we leverage this large model and initialize from it, then we can do much better. And here what we found is that this stepwise approach is doing a bit better than the lower or average options. And the same trend, we saw it also across, this was on Gemma, we saw it also for like the other models and in few shot accuracy. And just like as a quick nice result that like we found that if you take the Gemma and I think it had 18 layers, that model, you split it in half, so you have like half of the parameters. Instead of 2B, you have 1B, and you repeat it twice in this recursive way, and then you end up like doing better than models that are equally sized and were trained even for much longer. So, you do this like simple recipe, you shrink your model, repeat it twice, and train only for another 15 billion parameters, 15 billion tokens, which is relatively short. You get a pretty good model for its size. So this was already like pretty good. We get like a pretty good Pareto frontier curve here, but we want to do even better. Like we want to get as close as possible to the full model. So the next thing we did is to relax a bit this constraint of parameter sharing. So yeah, this was like one novelty that we did in our work here, is that instead of just repeating the exact same layer, what if you can have some additional parameters that specialize specifically on the role of, you know, the different loop iteration that you're in. And it turns out that you can do it with LoRa adapters. So, you know, LoRa adapters usually are used for different setup, for like for like training optimization. But here we use it for you know, having a single layer that has like different hats that is like being used for different stages of the model. And unlike like regular LoRa that, you know, we usually freeze the full model on only train the LoRa, here we train everything together. And this can like still be served relatively efficiently, even if you like repeat the loop twice but have different LoRa's. So again, you know, the natural question again was like, how do you initialize those LoRa's? So like regular LoRa's, you initialize like the A matrix randomly and the B to 0. But here again, like we already have a target model that we are trying to mimic. So maybe we can utilize it better. So we like, you know, we know here that we're trying to get as close as possible to layer 4. So, you know, we can just do SVD and initialize the LoRa parameters based on that. So yeah, so that's exactly what we did, and it turns out that like it works pretty nicely. So, you know, with the LoRa, it is doing a lot better. And here actually the trend switched, that like when we did average utilization for the main layer, it worked better with the LoRa on top. And also this like SVD utilization worked better than starting from a 0 LoRa. So yeah, so just like to tie it back again, like we have like a couple of knobs here. We have like, you know, how many recursive iterations we break the model into. And now when we have this LoRa, we also have this like knob of like, what is the rank of the LoRa's that we use. And, you know, unsurprisingly, generally, let's look at the average. Generally, the higher the rank we use, then we get better performance. And after we do this and also like do a slightly longer training and also knowledge distillation from the full model, then we can kind of like recover the performance of the full model while still being smaller than it. So we're like 20% smaller and we're getting the same performance as the model that we started with. And we're not only smaller, we're also now doing this like recursive style inference. So we can go back and apply this like depth-wise batching and get even better speedups. Yeah, so like, you know, just to show back on the 3 different models, we get pretty nice trends here. With the tiny llama, we even get better than the original model. So, you know, with not too much extra training, we get pretty good results with this recipe. Yeah, and as I said, like tying it back to the depth-wise batching and like early exits. Sorry, so now we can add early exits to the inference, and you know, we get almost the same accuracy, but nice speedups that hold also for large batches. Yeah, so that's all that I wanted to present, just to, you know, tie everything together. Early exits are a nice technique for like leveraging the fact that like not all the predictions have the same difficulty. So, you know, you don't all like, it's nice that we have huge models, but we don't always need to use them for all the predictions. And there's a lot of like headroom to apply them in a more dynamic way that leverages the full capacity only for the predictions that matter. So we discussed about Calm, which is like one nice way to do it, to introduce these capabilities to models and also to control for the overall quality, and some kind of like different variations, improvements, or like different variations of like how you can apply it in different ways. And then finally, we discussed this relaxed recursive transformer work that specifically aims to reduce the number of flops that you apply for different examples, while nicely allowing you to do it in a large batch setup and preserving the performance of the full of the full model. Yeah, so that's all that I wanted to present today, and thank you very much for listening. I'm happy to take any more questions. Yeah, and if you are at ICLR, feel please come to our poster. Salmin will be there to present the work. And also feel free to reach out with any questions or ideas or comments.
Maybe just a quick question on the continuous batching. So now I guess there you do confidence thresholding after every block or so. And let's say there are 8 examples or 16 or so. I guess you compute confidence for each one of those, and only those that exceed it will kind of exit. Is that the case, or?
Yeah, exactly. Again, you need to implement it to be able for your serving implementation to be able to support it. But yeah, the idea is that after each of those blocks, let's say that you have those 3 recursion blocks, then you measure the confidence over your instance-wise over all your examples in the batch, and then all the examples that are above the confidence threshold, for them you stop and you go to the next time step, and then they continue from stage 1 of the next time step, while you continue for the following stages only for the ones that didn't exit.
And this is still on the token level, right? Everything here.
Yeah. So this is a simplified view, but yeah, in the token level.
Okay.
Yeah. All right, going once, going twice.